All right, welcome to Module 4, and we've got 2.5 through 2.7. Let's go ahead and dive in and see how far we get. We only have 3 sections, but this might be split up into 4 videos just based on um, the density, so to speak, of this section. But let's see what we mean and just dive into it. So, what we're going to talk about first are hopefully some of these things you've seen before. In other words, in some of your problems or working things out, you've seen x squared, you've seen absolute value. But what we're now going to do is we're going to talk about what we call parent functions, where if we only see, or the most, I guess I'll say, the most interesting thing we see in an equation is a square root, or maybe there's no exponents or anything, or maybe there is an absolute value, or there's a cubed or a squared. What does that graph look like in general? And then what are the things we can do as mathematicians to shape where that graph goes or change its appearance? And so we'll see what we mean by that in a second. So the first thing we need to do, and we're going to do this quickly, but you should spend some time and really think about how we got these by simply really making a table, so to speak, on the left in our heads. We're not going to write it out, but we said when x is 0, I got what? And if I plug in 0, I get 0. And then if I plug in 1 for x, well, then I know the answer for y, it's also 1. And so I graph the point 1, 1. Guess what? You're going to get the same thing for 2, 2, 3, 3, so on and so forth, and it goes for the negatives as well. Now, this shouldn't be surprising because after all, this is simply, if we take some of our prior knowledge, this is simply mx plus b, where m is equal to 1, the number in front of x is 1, and b equals 0. So that shouldn't be surprising that that's the line I graphed, because there's my y-intercept at 0, and then there's my perfect slope of 1 over 1, up 1, right 1, or down 1, left 1, like we talked about in the last section. So there's y equals x. It's just a line, but in other words, this is the most simple line you could graph. A perfect diagonal positive slope and a y-intercept at 0. And then that brings us to the absolute value of x. Now, this one actually starts, so to speak, pretty similar. When I plug in 0, I get 0. When I plug in 1, the absolute value of 1 is 1. When I plug in 2, I get 2. When I plug in 3, I get 3, so on and so forth. But look what happens when I plug in -1. When I plug in -1 for x, I'm going to end up actually absolute valuing that and get +1. And so we end up getting this shape, which goes on and on. Now this is, again, in essence, the most basic, or the parent, absolute value graph. And the way we would describe this is its vertex, we'll learn what this means later on, but its vertex is at 0, 0. Now, in other words, I want you to say it this way or know it this way, that for an absolute value graph, the vertex is either the local min, or in this case, it would actually be the absolute min because it never goes lower, or depending on how it gets shaped around or reshifted, it could be your local max. All right, let's keep on going and let's look at x squared. Well, once again, when you plug in 0, you get 0. When you plug in 1, you get 1. And finally, something's about to be different here. When I plug in 2, careful, you're plugging in 2 for x, so you're getting 4 for y. And we're already about to be off the page, so to speak, because if I plug in 3, I get 9. Now notice that this so far um, is not going to be a straight line. This is the first curve that we're going to see. And hopefully that sounds familiar, that we're looking at what we call quadratics or parabolas. Now let's go left. If I go left, if I plug in -1, I still square that and get +1. If I plug in -2, I will square that and, careful, still get +4. And if I plug in -3, I will square and get +9. And this is going to be what the parent function of x squared looks like. Once again, I want to point out that there is a vertex on this as well, it's at 0, 0. The other thing that's worth pointing out, just to use some vocab, is hopefully we realize that the absolute value of x and x squared would be what we call, again, even functions because they're symmetric with the y-axis, just pointing that out. All right, two more. We get to go a little more quickly. When I plug in 0, guess what? You still get 0. You can square root 0. It is just 0. When I square root 1, I also get 1. Now here's the thing, when I square root 2, I don't get something nice and clean. When I square root 3, I don't get something nice and clean. But when I square root 4, I get 2. And when I ultimately end up square rooting 9, I get 3. And so here's what, whoops. Here's what the square root of x looks like. And what you should be saying or thinking, or rather what you could be saying or thinking, is, hey, that kind of looks like x squared just tilted on its side. And the short answer is there's a reason from that, and that's 2.7 that we'll get to. Um, from there, let's look at y cubed. This one goes by quickly. Again, plug in 0, get 0. Guess what? Plug in 1, you get 1. But if you plug in 2, wow, you get 8. From there, what if you plug in -1? When you cube -1, you actually do get -1. And when you cube -2, you end up getting -8. The reason you get negatives is because you just multiplied a negative to itself 3 times. And so that means a triple negative would stay negative. And this would be your graph. Now, the way to kind of, I don't know, think about this is it kind of looks like x squared, only it didn't have a, solid vertex, a low point or a high point. It does kind of have this center point where interesting things happen and symmetry occurs. By the way, this has odd symmetry, just to point that out, to say that vocab. The other thing I want you to look at is that it almost looks like this is x squared, only instead of it flipping up in both directions, one time it went up and the other time it went down. Hopefully that kind of makes sense how I'm saying that there. Now, the thing that's important is that you learn to commit these to memory and you learn and understand what those first basic few points are. That when I graph just a regular line, I just get a perfect diagonal starting at 0. When I graph absolute value, I get this perfect, still diagonal, right? It is based off lines. It's just I started drawing a line like normal, but instead of dipping into the negatives, I flipped on what's called the vertex, and we'll look at how to identify that as we go through, and then it ends up going upwards instead of continuing down into the negatives. All right. With all that being said, this is your first goal, to memorize all these. We've only spent 8 minutes on these basic graphs, but it's really important that you commit these shapes to memory because we're about to transform them. And so we're not going to waste our time writing all these rules down. They're here for you. But what we're now going to do is we're going to say, I can take that central point, usually it's referred to as the vertex, and if I look at what happened to the function, or rather if I look at what happened to x, or if I look at what happened around x, I can identify changes in that parent function. And so, what I want to point out is we can either see we can either see addition or subtraction happening not to the x directly. I guess, how do I want to phrase that? Rather, we can see plus or minus something that's creating a second term. Yes, it's not happening directly to x. Or, watch this, we could see plus or minus happening in the thing that gives the function its name, is what we're going to kind of say there. How was that function named, and is the addition or subtraction occurring in there? Well, if that happens, you're moving horizontally. And also, things to look at really, really quick is notice that for outside of the main name of the function, a plus or a minus moves as you would think it would. A plus goes up, a negative goes down. But take a look at what happens when you're transforming inside or in the thing that gives the function its name. A plus actually moves you left, and a negative actually moves you right. Interesting. There's ways to reflect over the x-axis and reflect over the y-axis. Again, is it happening outside of the thing that gives the function its name, or is it happening inside of the thing that gives the function its name, and that will tell you which answer is which. And finally, are you having something multiply outside of the function, or are you having something multiply that happens inside the function? I will tell you that I'm pretty sure we don't really see much of this in your homeworks at all. So just wanted you to be aware of that. So the very last one, I wanted you to, oh my gosh, there's the pun, be aware of that, that you likely won't see that in your homework. All right, well, after that bad joke, let's dive in and see what's going on here and what we mean. Once all of this clicks, once all of your parent function graphs are settled and you've careful committed this as close as you can to memory, the rest of this is smooth sailing. We just did a lot of buildup. So here we go. The thing that makes this function what it is of course the x being squared. And the question is this minus 4 happening in the thing that gives it its name, or is it happening afterwards? And hopefully you would say that it does indeed happen afterwards. So this negative 4 is right up here is what's going on. All right. So this graph is being, we would say, moved down 4 units. All right, so I'm now able to just read the equation and identify the change I'm going to see. Now the question is, what does it mean to move down 4 units? Well, remember what our parent function x squared looked like. It had that parabola shape starting at 0, 0. And so from there, I'm first going to take that point 0, 0, that vertex as we called it, and we're going to move it down 4. There's my new vertex. The question is, now what do I do? And the answer is now I essentially recreate that shape. And so let's kind of move beyond just plugging numbers in. Let's talk about what a squared or quadratic or parabolic shape looks like. From your vertex, unless you're stretched in other ways, you're going to then move right 1 and up 1, right 2 and up 2, sorry, up 4, because we're squaring. That's the thing that gives it its name. And from my vertex, again, the vertex moved down, I can then move right 3, and then I would move up 9, which, let me see, yep, counted that right. And guess what? When I move left 1 from the vertex, it squares and goes up 1. When I move left 2 from the vertex, it squares and goes up, oh, that's where it was, up 4, which would take me back to 0. I knew one of those was off. There we go. And then when I move left 3, I square, and I end up going up 9. So it's the same quadratic shape, it's just moved down 4 units. Now what you could also do, but again, this is what we're trying to move away from, is you could, of course, plug in 0, 1, 2, and 3 directly into this and work out all the steps and see how we got here. The idea, though, is that we're now moving on and we're not going to plug stuff in. We're going to memorize the basic shape and understand that I can see that that's going to be my basic shape. It's going to be this parabola shape. It's just moved down 4 units. All right, well, now we get to really get moving. Let's look at this transformation. Where is the shift or change occurring? I see a plus or minus, so I'm definitely dealing with one of these, but this time the plus or minus is inside the thing that gives the function its name. This is a square root function, and the addition is happening in the square root, which means I'm encountering this rule where we would denote that as plus or minus c. Now, because I see plus 4 inside the square root, I'm looking at this, which now tells me I must be moving left 4 units. So this graph moved left 4 units. Just so you also know, you might see it in your homework, when we move left, right, up, or down, we call those translations. Well, and it literally says that in the chart there, but just wanted to say that out loud. Maybe that was just subconscious that I was reading it, but they are called translations. Um, well, what does that square root graph look like? Well, if you remember, originally it looks like 0, 0, 1, 1, 4, 2, because it's that squaring in reverse, and then it would be right 9 up 3. So it would have this shape. Well, I'm going to take that shape and I'm going to move its starting point 1, 2, 3, 4 units to the left. And from this new point, I'm going to move right 1 up 1. From this new point, I'm going to move right 4 up 2. From this new point, I'm going to move right 9 up 3. And this is why we call, again, just to go back to the last page one time, this is why we call them the parent functions. Because once you memorize these shapes, anything else you do is really just a matter of sliding it up or down, so to speak. Like if I had a little transparency piece of paper, in fact, that's usually an activity you kind of do in Algebra 1 or Algebra 2 when you first encounter this concept, is you take wax paper and draw this shape, and then you literally take your hand and move it around, is a good way to visualize what we're doing with those pluses or minuses on the outside or the inside. But of course, things can get trickier. And we're almost done as well. So now we're looking at this function, and there's a lot of things that have happened to it. And in fact, there are 4 things that have happened to it, and it might be worth uh, your time to pause the video and see if you can identify those 4 things that are occurring. But I'm going to assume that you have done that and tried it out, and so here we go. The first thing, to kind of go in order of kind of what we're identifying top down, is I first see a +4 on the outside, which would mean that at some point this graph, whatever its parent shape is, hopefully you know, it's going to move up 4. And then, because I see a -5 on the inside of my absolute value graph, the thing that gives it its name, this must be a right 5, because when the plus or minus is on the inside, it is the opposite of what you see that you name it. So a minus on the inside is moving to the right. A positive on the outside is moving as expected up. From there, there's 2 more things happening on the outside. So notice that it's not just that it's -2 being multiplied. No, catch this. It's that there is a negative, so there is a reflection over the x-axis, because there is a negative, and then there is a, catch this, vertical stretch of 2. All right. So again, what we're calling out there is that there was a negative outside of the absolute value. So that's why I called it like that. And because there was a multiplication happening outside of the thing that gives the function its name, outside of the absolute value, watch this. The question is that number itself larger than 1, ignoring the sign? Yes, it was. And if instead it was like 1/3 or 2/5 or whatever, then it would be called a vertical compression. That's what that's saying is that number out front, ignoring the sign, right? That's what an absolute value is. Is it either bigger than 1 or is it between 0 and 1? Is all we're saying there. Okay. Now, from there, let's once again, just really, really quickly, look at the parent function of absolute value of x. It's this basic V shape, so there is a lowest vertex point. And so what does it mean to take this graph, move it left, right, vertically stretch it, and flip over the x-axis? Now, also, we need to talk about PEMDAS. Remember that PEMDAS would say multiplication happens first. So these two are actually occurring first. So we're flipping over the x-axis, then moving that vertex point. Well, where does that put us? Goodness. Let's see what happens. Well, from where my vertex used to be, after I've reflected and stretched, I would have at some point taken that vertex point and moved it up 1, 2, 3, 4, kind of going in order of what I said, and right 1, 2, 3, 4, 5. Okay, now, if I didn't have these two, what I would do is I would then make that perfect diagonal V right here and I'd be done, but I'm not, because now this positive upward V shape is going to flip and go down now because it already was reflected over the x-axis before we moved it around. So now imagine it's opening down like this, But not only that, it's not going to be a perfect diagonal anymore. If you want to think about it this way, it's going to be a slope to the right of this vertex of down to right 1. So imagine that being your slope of like a regular old line, move down to right 1, and from this vertex point, I could then move down to right 1 again. And from there, finally, here's where the V shape shows up, but it's flipped now. I could go left 1 from here, and I would then move down 2 because there is that symmetry in this graph. So based on what I can fit on the page, this is what I get, and that's my new graph. So hopefully you can kind of see those four transformations again from that what used to be perfect V shape. We flipped it first because multiplication occurs before addition or subtraction. We flipped it. We then stretched it. We made it a literally like a how do I say it? It's a, well, literally vertically stretched 3. Imagine I took that perfect diagonal and stretched it. So now it starts slanting down more aggressively. And then from there, we then moved it at some point right 5 and then up 4, and that was our graph. It takes time to process and get these things, but here we go. Let's look at the last two really, really quickly here. They don't take too long. So there's two more transformations occurring here. We've got a negative on the inside. That's going to reflect, whoops, over the y-axis. And then we're going to move down 4 because that subtraction happens outside of the thing that gave its function its name. Now, what I'm calling out here also is that that negative happened inside the thing that gave the function its name, so I now know I'm reflecting over the y-axis. All right, really quickly, what's happening there? Remember that this is our square root graph, so at some point it should have looked like this. But because I'm reflecting over the y-axis first, because again, multiplication, that is multiplication, happens before subtraction, instead of opening this way, it reflects over the y-axis and opens this way. And then I take that basic shape and move it down 4 units. So here's my new start. And from this point, again, the parent function used to say go right 1, up 1, but now I'm going to move left 1, up 1, because I reflected over the y-axis. I used to go right 4, up 2, now I'm going to go left 4, up 2, and that'll be enough there. So once you really, really put these and kind of commit these charts and the parent functions to memory, you can see how fast these can go, but the question is how good did we do memorizing? All right, last two. This one is going to be moving left 6 because the plus is happening inside of the thing that gives the function its name. And so when it's plus on the inside, it's the opposite of what you expect. Finally, there's a negative, which again would apply first before we move left or right. And that's going to again be a reflection over the x axis. All right, well, I know what that basic cubic shape looks like. It looks like this. And from there, I'm going to reflect that over the x-axis, so that would now look like this. I'm not drawing it yet, but I've reflected over the x-axis, and I'm now moving that left 6. So I'm now over here, and remember, from that special point, I went right 1, down 1, right 2, down 8, and I could do the same thing in reverse, because I know that this graph has symmetry. And there we go. This graph was reflected first, right? Was reflected first and then moved left 6. All right. That was a lot to cover, but we did it. I'll see you in the next one.